So far, when we've been discussing waves, we have just been thinking that our waves have only one velocity, our wave velocity v or c in our equations. However, in many situations with classical waves, we have to think about what happens when waves of different frequencies travel at different velocities. This phenomenon is called dispersion. In ordinary classical waves such as sound or light waves, this is mostly not a major phenomenon in many simple situations. But this dispersion is far from a negligible phenomenon in some particular situations we do come across with classical waves. For example, when we send signals on light down the very long distances involved with optical fiber communications, distances that can be of the order of 100 kilometers, for example, we see quite undesirable consequences of even the small amount of dispersion for light waves in glass. When we send a signal down a glass fiber, in the simplest version, we're simply turning on and off a light beam in a set of pulses. In the simplest version of these communication systems, the presence or absence of some pulse of light would just represent a 1 or a 0 in some stream of bits. Now, from our understanding from the Fourier analysis we discussed briefly before, a pulse of light in time is also something that we could think of as being made up out of a set of waves of different frequencies. If those different frequencies of light travel at different velocities, we have two problems. First, what velocity do we now think the pulse is going at? The answer to that is something called the group velocity. Second, what will happen to the shape of the pulse as it propagates forward in the optical fiber? The answer to that is that in general it disperses, which typically means it gets wider in time as it goes down the optical fiber. That can be a significant nuisance because it may start to bump into the next pulse in our stream of bits. And we may start to get confused about what the bits are that are arriving at the far end of the optical fiber. Optical engineers need to understand both of these effects, of the group velocity and of the pulse dispersion. They need to understand them very well if they are to understand how their optical communications is going to work over the optical fiber. Now, while dispersion for optical waves is usually not a very strong phenomenon, and we only have to deal with it in optical communications because our optical fibers are so long, in the waves we have to consider in quantum mechanics, this phenomenon of dispersion is very strong. In fact, unless we understand this idea of group velocity, we really have no idea how fast anything is going. So let's look at these ideas of dispersion and group velocity in some more detail here.